So I've recently done a video on black holes where I looked at black holes that are not rotating and their size and density. I also mentioned that I'm going to do a video on the effect of rotation on black holes and bring to the picture the idea of possibly naked singularities existing in our universe. But a good in-between video is a video that looks at the effect of rotation on objects that are less unusual, shall we say, than black holes, such as stars. So in this video we're going to look at, are all stars spherical? And we'll see that actually their rotation plays an important role in determining this. And we'll see an example of one star which, against all odds, thanks to its incredibly high angular velocity, would not be spherical, to a good approximation anyway. So that's where we're going in this video. It's a good in between black holes that aren't rotating and black holes that are, and it's also a fun bit of kind of astrophysics and a good application of the idea of centrifugal forces, which you might have heard about if you're doing kind of A-level physics. And so this is a fun application of things like circular motion, something more novel perhaps than things like, roller coaster rides and stuff. So now we've mentioned that there might be a possibility that in some extreme cases we have stars that are not good spheres. Let's talk about the force responsible for this. And this force is a fictitious, also known as a pseudo-force, called the centrifugal force. Now, if you've ever been on something that's rotating, if you've been on those park rides where kind of like there's a central large column that spins, and then you're kind of like, start, swinging around this kind of central column, then you'll be familiar with this feeling. Also, if you're on a roundabout, you feel like there's a force trying to push you away from the centre of the rotation of the roundabout. Now, this force is fictitious in that it exists for you if you're rotating, because if you're rotating, your perception of the world is rather different to somebody that isn't rotating. So fictitious and pseudo forces are forces that appear in one reference frame but not in another, because they result from, the dynamics of a particular reference frame, not because of any actual physical interaction that's occurring. And we can see that, stationary observers seeing something, rotate or orbit wouldn't think that that thing is feeling some kind of, centrifugal force. Because, when, we send a satellite into space and look at the Earth, it seems like the Earth's acceleration, judging from the Earth's change in velocity, is always pointing towards the Sun, generating a gravitational pull. The acceleration of the Earth does not seem to be away from the Sun. So for a satellite looking at the Earth, there is no kind of force on the Earth trying to push it away from, the point it's orbiting around. So the satellite wouldn't say that the Earth is experiencing a centrifugal force. It would say it's experiencing a centripetal force. That's a force that actually genuinely does exist, at least from the perspective of, a stationary observer. And that centripetal force is causing the Earth to accelerate towards the Sun, but, there's no acceleration away from the Sun. Now, as I say, the centrifugal force does not exist as far as a stationary observer would consider, like a satellite watching the Earth orbit the Sun. However, what is stationary and what is not is a fairly relative concept. And so, say you're on a roundabout that's spinning, you could argue that you are stationary. You most definitely could describe a consistent picture of the world where you are stationary. Now, whereas, velocity is kind of so relative that actually, saying whether you are or are not in motion doesn't result in the creation of any forces. Acceleration is different. Acceleration is still relative, but it's not a trivial statement to say something is or is not accelerating. And so the result of kind of you claiming that you are stationary or experiencing the world as if you are stationary, when you are rotating, is that you have to introduce another force in your reference frame as a result of your insistence that you're stationary. You can also think of it like if you add the centripetal force that everyone agrees exists, with the centrifugal force which you believe exists, you would conclude that the total resultant force on you would be zero, implying that you would be, at least not accelerating or stationary, which is what you are claiming in your own reference frame. So, a stationary observer agrees on the centripetal force but not the centrifugal force, whereas you, as a rotating observer, because of you insisting that you are not accelerating and that not being a trivial statement, is going to be experiencing an additional force called the centrifugal force. And that centrifugal force allows you to claim that your acceleration is zero, and therefore to have a picture where you potentially stationary or at least not accelerating. So I'm talking about that in a bit of detail because a lot of the time it said the centrifugal force is fictitious or pseudo force, and it's not really explained what that means and particularly whether this force is or is not real. So it's worth having a slide talking about the nature of the existence of this force and it being related to reference frames more than any physical interaction. At some point I'll hopefully do a video deriving the pseudo forces, including the centrifugal force, but for now we're just going to take it up front that there's a centrifugal force. For a rotating observer anyway, from their perspective, or an orbiting observer. Although we'll be talking about rotating suns for this video, we're talking about really rotating observers. Now, for the rotating object to consider there to be no resultant force acting on it, the centrifugal force has to equal the centripetal force. And therefore, when you're calculating the centrifugal force, which will be pushing, material in the star outwards, or at least attempting to, we can claim that that centrifugal force in size is equal to any centripetal forces that might exist. That's important because, in calculations, we often kind of cheat. When we're interested in the centrifugal force, we calculate the centripetal force, but as I said, their size has to be the same. Because the centrifugal force exists to allow the rotating observer to claim that they are, in fact, actually not experiencing any resulting force at all, and therefore not actually accelerating. So now we've had a little bit of a talk about the centrifugal force, let's talk about how the centrifugal force can cause a spherical object to become non-uniform and to cease being a sphere if that object starts to rotate, such as, for example, a fast-spinning star. Now, to do this, I'm going to start with an assumption that at time t equals 0, the star is perfectly spherical and is not rotating, and then we're going to consider what effect future rotation has. So at t equals 0, the star is completely spherical. So if we take a a kind of slice through the star, we have essentially a circle. But the star as a whole will be a sphere. And the radius of the star is given by capital R. Now the radius of the star is constant, and for simplicity I'm just going to assume that all of the material on this star is either evenly distributed or all lies on a spherical shell, just for simplicity. But we can look at this star and break it down into kind of disks which are perpendicular to the axis of rotation, so perpendicular to the blue arrow. And you'll notice that these disks, because the circumference of these disks are required to lie along the surface of the star at a fixed coordinate along the axis of rotation, these circular disks will actually change in size or in radius as we move, say from the centre of, from the equator to the poles of our star. And so whilst capital R, the radius of our star, isn't something that is a variable, small r, the radius of one of these disks, is variable, and its size depends upon kind of its position along, in terms of the coordinate for the axis of rotation it's on. Now, if the star starts to spin, then since these disks at different points in the star will have different radii, they will spin at different rates. Because, for the star to stay together and to, rotate, coherently, each disk is going to take the same amount of time to complete one full revolution. However, some disks are larger than others, and therefore will have a larger circumference. Hence, material on that disk will have to travel faster to cover that circumference over the fixed time than material in disks with smaller circumferences or radii. And particularly if we look at the disk on the equator, that's a huge circumference it has, and therefore the material in that disk is going to feel a huge centrifugal force comparatively to disks much closer to the pole. And if we want to quantify this, we can use things like the metric tensor from tensor calculus, where, as I think I've done in another video, you can show that the circumference of a kind of circle, I should say the circumference of a disc on a spherical object, which is at angle theta, to the axis of rotation. So in other words, the disk I have shown in the diagram of the blue star, the circumference of this disk is equal to 2 pi capital R times sine theta. And you can also use kind of trigonometry to work that out, because as you can see from the diagram, capital R and lowercase r are kind of by definition perpendicular to each other, so we can form a right angle triangle. And therefore, just using the definition of the sine function, you can deduce that this relationship is true as well, without having to go through the whole rigmarole of metric tensors and polar coordinates. Now, we're going to make use of a quantity that describes how quickly the star is rotating, and that quantity is called omega. And omega is equal to 2 pi times the frequency of the kind of star's rotation, which is 2 pi over the time period, so the amount of time for the star to rotate. And bearing in mind each disk is rotating, with the same time period, and therefore the angular frequency of rotation is constant throughout the star, except really at the poles, because at the poles our disk will have a size of 0, and there will be no rotation, because the poles lie along the axis of rotation directly. And the kind of like velocity in terms of distance over time that matter on a disk moves is equal to the circumference of that disk divided by the time period, which, using our definition for omega, is simply omega times small r. And if we put that into a formula for the force associated with the centrifugal, or if you like to think of it in terms of centripetal, or so the centripetal force, we have kind of this equation linking the force F with the angular frequency omega, and now substituting in the fact that for a disk at angle theta relative to the axis of rotation, the velocity of that material moves in that disk is equal to omega capital R sine theta. We have the force, the centrifugal force matter on a disk at angle theta would feel is equal to m omega squared r sine theta, which, when theta is 0, so at the poles that force is 0, but when theta is 90 degrees, so at the equator, that force has its maximum. And it's thanks to this kind of like force that matter on the equator feels like it's pushed out from the star more so than kind of matter at the poles, causing the star to cease to be spherical, and to become, as we say, the bright spheroid, essentially like almost like an egg in extreme cases. And now we're going to look at, given our equation for the centrifugal force, is the maximum centrifugal force, so the centrifugal force on the equator, we'll say something like Earth significant, and we'll see it's not, unsurprisingly, but then we'll look at a star where this force is comparable to the gravitational pull of that star, and therefore centrifugal forces will play a very significant role in the shape of that particular star. So, we said we were going to look at the Earth, so let's have a look at the Earth. And, the Earth is, almost, perfectly spherical, so as you might expect, centripetal or centrifugal forces are, very, very small, compared to the strength of gravity. Or we can rephrase that in terms of acceleration. So if we're looking at kind of like the acceleration due to centripetal forces, well, that's going to be maximum at the equator of the Earth, and using the fact that F equals ma and the equation we had for the centrifugal or centripetal force, we can clearly show that the maximum centrifugal acceleration is equal to omega squared r, and when you go through the calculation, given the radius of the Earth, you end up that the acceleration due to the Earth spinning, the acceleration that produces would be 2.53 times 10 to the minus 7 meters per second squared. And that is completely tiny compared to the acceleration due to gravity, which is about 9.81 meters per second squared. I mean, it really, it's like the centrifugal acceleration is about 100th millionth of the gravitational acceleration. So we can ignore the fact of the Earth's spin when we're calculating things like the overall force we would feel causing us to be attracted to the Earth's core. In other words, what we would experience as a weight, and we can also ignore the fact of the Earth's spin if we're considering the shape of the Earth. Now, this is pretty typical. I mean, our sun, for example, is incredibly spherical, as you can show by, calculating the acceleration of material on the equator of the sun compared to the, gravitational acceleration the material is experiencing on the sun. And I'll leave that as a task to you. You can get the gravitational acceleration on the surface of the sun using Newton's law of gravity, and you can calculate the centrifugal acceleration of material on the sun in a very similar way to how we've done it, for calculating the centrifugal acceleration of kind of material on the surface of the Earth. Another cool thing you can do with this is you can kind of consider, well, how fast would the Earth have to spin for the centrifugal acceleration to just exceed the acceleration due to gravity, and therefore, in other words, how quickly would the Earth have to spin for gravity to no longer be able to hold on to things on its surface and thus to fly away from the surface of the Earth. At some point I'll probably do a small video on that. Well, because it's going to be just a quick bit of calculation, I might put that on Patreon or something, but it's something you can have a bit of fun with and try out for yourself if you like. So now let's have a look at a really fast spinning star, because although it's quite rare, there are some stars out there which spin incredibly quickly. Now you might think neutron stars spin very quickly, and they do, but neutron stars have such a high density that this spin doesn't really affect their shape much at all, because their gravitational field strength on the surface is so whoppingly huge. I mean, the escape velocity from the surface of a neutron star is, a significant fraction of the speed of light. So, these are their gravity is, overwhelming. But there are some, more traditional stars out there which spin incredibly quickly, and the one I'd like to introduce you to for this video is the 10th brightest star in the night sky, a fascinating star called Echina. Now I might be pronouncing the name wrong, it might be Echina. If I am, I do apologise, but I'm going to be calling it Echina. But for our purposes, its name is nowhere near as important as its spin. Now this star spins a lot faster than the sun. So Echina, which is in our fairly local neighbourhood, it's about 139 light years away, which if we're considering the size of our galaxy, isn't really that far. And this star spins once every 2 days. The sun, on the other hand, takes about 27 days, I think, to form to do one, complete rotation. So this star Achernar is spinning incredibly quickly. And using that time period, you can get a value for the angular velocity, or angular frequency, omega, which is about 3.64 times 10 to the minus 5 seconds. Per second. Now, because Achernar is, not, practically next door, even though it's still fairly close by in astronomical terms, there's some, uncertainty with regards to its radius and its mass. So if you look at the radius and mass of Achernar online, you might get slightly different values to the ones I'm using. But I've tried to pick as far as possible a fairly average value. So gone with the radius of Achernar having 9 times the radius of the Sun, which seems to be about the middle ground for approximations of the radius of Achernar. Which leaves the radius to be about 6.26 times 10 to the 9 meters. And that gives us a centrifugal acceleration of 8.29 meters per second squared. Now, admittedly, Achernar is a lot heavier than the Earth, but this acceleration is way larger than the centrifugal acceleration of the Earth. So it seems pretty promising. But as I say, Achernar is much heavier than the Earth. So before we get too excited, we need to calculate the gravitational field strength on the surface of Achernar. And taking the mass of Achernar to be about 7 times the mass of the Sun, which is again a kind of average value for what I could find, we get that the gravitational field strength on the surface of Achernar is about 23.7 meters per second squared. So still larger than the centrifugal acceleration. So, Achernar is still stable, it can still hold itself together, but the centrifugal acceleration is a significant fraction of the gravitational field strength, meaning Achernar would not be perfectly spherical, and wouldn't even nearly be perfectly spherical. And another interesting effect of this, centrifugal acceleration being significant is this centrifugal acceleration, which we have, which is the maximum centrifugal acceleration, so the acceleration on the equator of Achernar. This acceleration will mean that you're quite light on the equator of Achernar compared to how heavy you would feel on the poles. Because on the poles you've got the strength of gravity pushing you down, but no centrifugal acceleration to fight that, whereas at the equator the resultant force you would feel would be, significantly less than the gravitational force pulling you, or attempting to pull you to the to the core of Achernar. And therefore, due to the centrifugal acceleration, you're heavier on the poles than you are on the equator. And if you just look at the numbers, you can convince yourself that you'll feel about 35% lighter on the equator than on the poles of Achernar. And so an interesting property of this star is as you move across it, you would feel like you had, differing amounts of weight. You would feel, like here, different amounts of heaviness, if you like. So this has been really everything for this video on, are stars all spherical? The answer is pretty much all of them are very well approximated as spherical objects. There are a few exceptions like Achernar that are not, but the way that you would kind of work it out is you would compare the centrifugal acceleration to the gravitational field strength on the surface of the star. So that's everything for this video. I hope you got something out of it. Hope you've learned a little bit more about kind of astrophysics and approximations that go into astrophysics, such as the shape of astronomical objects. And I'm hoping to see you for more physics soon. And if you would like to learn more about stellar physics, stellar structure and evolution, I would recommend heading to the community page and selecting that option on the poll, because I'm hoping to do a playlist in not too long on one of 3 topics, and one of them was on stellar structure and evolution. So if this is the kind of stuff you want more of, I would recommend voting on that poll. But anyway, hope you have a lovely week, and hope to see you for some more cool physics soon. And yeah. And if you'd like to check out more stuff, then I've got lots of stuff on this channel. I've also started doing some stuff on Patreon. But yeah, there's a lot of material both present and also coming up.